And good morning, everyone.
Good morning.
Good morning.
Morning.
Good morning, Janae. All right, let's get that poll up and running. I think everyone will appreciate it today. So we talked about this on Monday, I believe. You got 1 minute to answer today's daily quiz question. Do we have class this coming Friday? Let's see. Nope, frozen. Now it's frozen. There is technically a yes and or correct and incorrect answer here. All right, it looks like I got most people in. I'll give you, what's up, Janae? So it's, you gotta, I know you're just running a little bit late today, but they always start and always end at the same time. Okay. So I'm locking answers here in 5, 4, 3, 2, and 1. Locking answers now. Ooh, some people are not looking ahead and just doing day by day. What's the answer?
No.
Yeah, there is no class this Friday. Why is that?
Yeah.
It's a holiday, right? So we still have class the following Monday. So the Monday after Easter, we still have class. So make sure you're still here. That'll be our second to last big long Monday. Okay. All right. Any questions before I begin today? Increase that. So I'll go shut off the lights. All right. So let's see. I do 100%. Hopefully that won't screw it up. Sorry, I wasn't here to get the lights for us today. All right. Today we're going to start talking about what is called analysis variance or ANOVA. It's a pretty popular test to see in any field, and it deals with when you have multiple treatments. So what we're going to see is if, in the example we're talking about today, we're going to be going through today, is if you're measuring the weight gain of lambs over 2 weeks, you give them 3 different diets. That's 3 different treatments, right? They're given diet 1, diet 2, diet 3, and we're trying to determine if there is some difference between the diets, okay? So it's going to be a little bit different in that we're not just considering 2 different populations like we had before with kind of like a chi-square test or a t-test, right? Where our null hypothesis for those, no matter which way you go about it, whether it be a pair t-test or standard t-test or a chi-square test, is that your 2 population means are the same, okay? Oh, and I guess I should have said, I just got this. If you want to go ahead and download this PDF, it's up on Blackboard now, and then also an R file if you want it. So I just put it up like 5 minutes before class though. So what if instead of just having 2 independent samples, what if we had I independent samples? So 3, 4, 5, all the way up to 10. So then we want to see, okay, is there a difference between them? Now, we don't necessarily want to compare all 3 or all 4 in pairs, because one, you get into a little bit of data snooping, right? You're trying all possible combinations, so you're bound to find something. But also, when you do comparisons like that, you end up increasing the probability of your type 1 error, right? So sending that innocent man to jail concept. And because of that, because our type 1 error increases if we do a bunch of different pair testing, then we want to make sure first that overall at the overall level, right? So between every single thing, that there is some noticeable difference between means. If we can find a noticeable difference between means, then that warrants further investigation into looking at all these pairs. Okay. So the null hypothesis we're going to be considering is the following, where all the population means from all the different independent samples that we get, I different independent samples are the same. So that's where you see this mu naught. Whoops, I need to be writing. Mu1 is equal to mu2 is equal to mu3 is equal to all the way to the very last population mean that we get from our last independent sample. Okay. So we're wanting to do this type of comparison. We're going to use this test called analysis of variance, or as short, ANOVA. So AN for analysis, the O for of, and VA for variance. Okay. I'm going to go about it a little bit differently because this is one criticism I've had of the textbook. Here's what you need to know before you can even do an ANOVA test. These are the assumptions that you have to satisfy for the results of it to be accurate. Is that the data must be considered as random samples from I different populations. So each sample is a different population. Okay. And then the harder one to really satisfy is that of those population distributions, those I population distributions, we need that they need to be approximately normal. And then also on top of that, the populations need the same standard deviation. So the spread of the data is also going to be roughly the same. Okay. I don't want to be comparing 2 population distributions. They could be approximately normal, but one has a very narrow peak, so it doesn't have as wide of a variance, whereas another one could be very, very wide. So the data is much more spread out in that second population. Okay, there are ways to get around this assumption, something called Welsh ANOVA. Doesn't require that assumption, but its statistics are a little bit different to calculate. My goal for today is to get you introduced to what ANOVA is doing so you can understand how this test is going about getting its p-value and then how we interpret the p-value from it. All right. And the other reason I put that note there is if you're dealing with observational data, it's almost impossible to actually satisfy that equal standard deviation assumption, right? You cannot be guaranteed that they're going to have the same standard deviation. So if you're wanting to do some ANOVA stuff for your course project, Welsh ANOVA is something you're going to want to have to look into. So we're going to start with what is called one-way ANOVA, and then probably on Monday we'll pick up very quickly two-way ANOVA. All the difference is you add in a different group. Okay, so you can add in an extra group instead of just one. But we're still going to have I different populations. So with one-way ANOVA, we're going to just start doing some notation that we're going to see because it's going to be necessary. This is definitely going to be a notation-heavy day. Okay, so I've tried to explain it all out. We're going to try to also dissect it because when we write notation in mathematics, we're not trying to just make it as obscure as possible. We do try to make it informative. Okay, It's just going to be different. So we have to start making sure we're kind of translating the mathematics into the English language in our head. So first things first, capital I, we're just going to let that be the number of groups that we have. Okay. Once I understand the number of groups I have, within each group, I'm going to have a certain number of observations. Okay. So we're going to still let n represent the sample size, but I'm going to put a subscript there. So that subscript can be 1, 2, 3, 4, and so on, and what that's going to correspond with. So if n1, sample size of group 1. If I had n2, that's going to be the sample size of what group?
Group 2.
And so on, right? All the way up until n with a subscript of a capital I, that's sample size of what group? Group I. Now, these are all observations, whether or not I can split them up into these groups. They're general observations for some observed variable, some y. So we're going to end up needing a double subscript here. So I'm going to zoom in just to make sure it's very, very clear. So I'm talking about this right here. You're going to have a y, and then as a subscript, you're going to have one number and then a second number. So that's where you see this y with the subscript of I and j. The j is telling you what number observation that is of that certain group. Okay, so in each group you have a different number of observations, and what that's just saying is, okay, I can say observation 1 from group 1 is different from observation 1 from group 2. Observation 1 from group 3 and different from observation 1 of group 4, and so on. And then for each of those, we're going to have each of those groups, we're still going to have a mean, right? We're still going to have, as long as it's numerical data, some mean for that group, and we're still going to use that overline notation, so that bar over the lowercase y, to represent a mean, but then I have to make sure I'm differentiating by group. So that's again where we're using that subscript notation, just like we did for the sample size. The I is just saying what group I'm in. So if I said, let's say, for example, y bar 2, what is that indicating? Sample mean for group 2. Okay. And then lastly, we're going to use that same subscript notation to differentiate between standard deviations of groups. So we're still going to use that lowercase s for standard deviation, but then the number for the subscript is just going to say what group it's coming from. Standard deviation for first group, second group, third group, and so on. Okay. So we're going to be using this notation a lot. We're going to define some things. We're going to see some notation. I'm also going to do my best to kind of give you explanation just kind of in the English language versus just the mathematical notation. But right now, are there any questions with kind of how to read some of this? All right.
Dr. Rapp,
Yeah, go for it, Amy.
can you just real quick re-explain why subscript IJ or JI or I'm sorry, IJ, thank you.
First one tells you what group you're in. Second one tells you what observation it is. Right? That's why in that description, observation J in group I. So each group has observations. So if I said Y11, what is that going to be?
The first observation for the first group.
Yep.
So the observations are as a group. So the
Mhm.
whole group would have the same observation
Say that one more time.
then. So in group one, for the first observation, that's just one data point, or is that a
Yeah.
group of data points?
That's one data point. Good question.
Oh, okay.
So go ahead and skip down here. So like the experiment, the example that we're going to do here in a second, kind of working with this and doing some of these calculations. So the lamb weights, you have 3 different diets, but notice that each diet has a different number of observations.
Okay, yes.
So right here, Y11, Y12, Y13. So all my observations from the first group, first, second, and third.
Okay,
And just for example, 2, 5 for that one.
I got you. Thank
Awesome.
you.
Yeah. Any other questions? Go ahead, Janae. So your second index is what? Yeah, so Y21. Whoops, not 25. It's I then 2. So it'd be 5-2. It should be 2-1, 2-2, 2-3, 2-4. So we're saying first one tells you what group you're in, second one tells you what observation it is. It wouldn't be Y2 what? Whoops, I already flipped that around. Yeah, it would be. So I had it right. You made me second guess myself. Because it's YIJ, or I is the group, J is the observation. All right. So some important calculations that we're going to want to do is one, say, okay, well, total number of observations. So we're always going to represent this with this symbol N with a nice little big old dot, solid dot as a subscript. Okay. That's going to represent the total number of observations that I see between all groups. And how I do that is just I add up all of the group observations or the sample sizes that we had. So I take the number of observations I had in the first group, add it to the number of observations I had in the second group, the third group, and keep adding them up until I get to the very last group. Okay. So conceptually, just add up all of your little group sample sizes together, and that's just going to be the total number of observations that you had. Now, it makes sense within each group, you're going to have a mean, but then because I can treat the data overall as different observations, I also want to be able to add up and find the mean of all observations, regardless of what group you're in. So there's a couple of different ways you can do it. This first one, this summation, this double summation right here, all it's saying is that first one indexes J, which means it's going through all of your observations. I is for the groups. So you said IB1, and then you go sum through all of your observations for the first group. Then you add up all of your observations for the second group. And then you add up all of your observations for the third group, and so on. And then I'm dividing it by that N dot, and again, that N dot represents the total what?
Number of all the observations added together.
Yeah. So this grand total is still that same concept of, what we're expecting for a mean. Add up all of your observations and divide by the total number of observations that you have. It's buried in this math notation, right? Looking at this double summation can be intimidating when you first do it. But all it is telling me here is just to add up all observations and then divide by the total number of observations that we have. Now, there's another way you can go about doing it, which is where you have that second equal sign right there. And it's just saying that, okay, if I went through and I calculated the mean for each of my groups already, all I have to do is go through and for each of those mean calculations, multiply it by the sample size and add them all together. So it'd be n1 times y bar 1 plus sample size times the sample mean for that second group. It's just a different way to go about doing that same calculation. I can just simplify some stuff that I have to do if I've already figured out what the means are for each of the groups. In either way, your goal is to add up all the observations and divide by the total number of observations. We're going to call that the grand mean. Okay. Any questions so far? Because I know notation can be tricky. It's a new language.
I'm confused on the double summation.
Okay.
Is it as
So you fix the outer one. And then sum equals 1 to ni. So I let the lowercase I be 1, 2, 3, 4, 5, and so on. So I'm going to be adding up y of ij. So when I break this down, it's going to add up into capital I number of summations, where I do first sum up all the observations in that first group. And then I'm going to add it to the sum of all observations in the second group. And then I add it to add it to the sum of all the observations in the third group. And I keep doing that until I get to the very last group that I have. So it's just saying, go through each one of those groups that you have, add up all of the observations. That's what I was trying to say, all observations up there. Does that make a little bit more sense to you now? Yeah. Awesome. All right. So then the last thing we have to deal with is, okay, well, I can get a mean for all of the data. How do I go about getting a standard deviation for all of the data? Okay. Well, there's a small issue in that I don't want to compare it to the grand mean. I want to compare them to their individual group means. And how I go about calculating the standard deviation depends on using a mean. It's the deviation from your mean squared. Okay, sum them all up, divide by the square root. So one of the ways to go about addressing this concern is to calculate something called the pooled standard deviation. And again, there's two ways that you can go about doing this calculation. They're both equivalent ways of doing it. I think I would say I prefer you to do this very last one. Okay. So what it's saying here is for each of the groups that you have, you're going to sum up the number of observations you have for each group minus 1. That's that n sub I minus 1. And then multiply it by that group's standard deviation squared. I keep adding all of those up. And then once I do, I divide it by the total number of observations I have minus, what does that capital I represent?
Number of groups.
Number of groups. So the total number of observations that I have minus the total number of groups. And then just to break this down, That summation notation there inside that square root is just saying, okay, for the first group, take its sample size, subtract 1, multiply it by its standard deviation squared. I'm going to add it to the second group, sample size minus 1 times its standard deviation squared. And then I guess I'll make it up here. N dot minus I is equal to total number of observations minus number of groups. And that standard deviation right there is going to give us a good idea of overall how all of this data is spread, right, across all the populations, all the different groups. So we're going to get practice with actually doing these calculations. But again, this notation is new for a lot of you. So do you have any questions for me right now? If not, give me a thumbs up.
S squared is the variance, right?
Yes, that's standard deviation squared is your variance.
Okay.
All right. So this is a fictitious experiment. The experiment was conducted on lambs to test their weight gain from eating one of 3 diets, and their weight was measured after 2 weeks on this diet. The results for the weight gains for each lamb in the respective diets is down here in this table below. So what I want us to do is just fill in all this information that we need. I went ahead and calculated the standard deviation for us. But then once I have the standard deviation, I also want to get the pooled standard deviation from all of this information. Okay. So first things first, I have 3 groups, which is the 3 diets, diets 1, 2, and 3. How many observations do I see for the first diet?
3.
Yeah, I see a total number of 3 observations, which means the number of observations I have for that first group is 3. What about for the second diet? How many observations do I have? 5. And then the last diet, how many observations do I have? 4. And this is one of the great things about ANOVA is that, I guess I can look up there for the time, is that it doesn't require that you have equal sample sizes. It's still going to work for unequal sample sizes. Okay. So now I want to say, okay, what is the sum of all the observations that I have for each group? So I want to sum up all the observations for the first diet, sum up all the observations for the second diet, and then sum up all the observations for the third diet. So for the first diet, what is the sum of all the observations going to be?
Well,
Sum of all observations is 12.
33.
33. I take 8, add it to 16. I'm going to get what? 24. Add 9. It's going to be 33. All right. Diet 2. What is the sum of all of its observations?
75.
What about for diet 3? Yep, 48. So from that, I can calculate a mean, sample mean for each of these diets. Well, what is the sample mean for the first diet? It'll be 11. I take the sum of all of my observations for the first diet, which was 33, divide it by 3, and I get 11. What about the mean for the second diet?
$15.
Take the total number of take the sum of the observations for the second diet divided by the total number of observations. 75 divided by 5 gives me 15. And then last but not least, what is the mean for the third diet? B12. Okay. So we had the standard deviations. One thing I want to ask is, I should have had the double line over notation. Yeah. What is the grand mean for this data? There's a couple different ways I can go about doing it, right? Since I already have the sums of each of my diets, easiest thing for me to do is just add up those sums. So the total value of the observations from the first diet plus the total value, or the sum from the observations in the second, plus the sum from the observations on the third. But then I need to divide it by the total number of observations that I have, regardless of diets. So how many lambs did we experiment on?
Oh.
It'd be 12. 3 plus 5 plus 4 is going to give me 12. So I take 33, add 75, and add 48, and divide it by 12, and what am I going to get?
13.
13. So I get that the grand mean for all of this data is 13. Now, essentially what this is saying is, if I didn't split this up between diets 1, 2, and 3, this is the average for my sample. But when I look at the averages for each diet individually, 11, 15, and 12, I say, okay, well, maybe am I going to see a significant difference from that grand mean compared for each diet? So maybe is 11 far off from 13, 15 far off from 13, 12 off from 13? We don't know, right? 1 to 2 pounds, that might not be significant difference, okay? That's what we're doing here, is we're comparing that grand mean to the different sample means. All right, last thing we got to do is calculate my pooled standard deviation. So the pooled standard deviation, we said, and I'll try to just scroll up a little bit. The easiest way to do it is just take each sample size that I had minus 1, multiply it by the standard deviation squared, add all of those numbers together, and then divide by the total number of observations I had minus the number of groups. So for the first group, again, how many observations did I have? 3. So I'll take the total number of observations I had minus 1 and then multiply it by the standard deviation for the first group squared, which is 4.359. And I'm going to add to it the information from my second group. So the sample size of my second group minus 1, or 5 minus 1, times the second group standard deviation quantity squared, which was 4.95. Then I do it for the third group. We had 4 observations, so 4 minus 1 times its standard deviation, 4.876 quantity squared. And I'm going to be dividing it by the total number of observations that we had across all the diets, which again is what?
12.
12. And then I subtract the number of groups that I had. And how many groups did we have? 3. So if you do this calculation, oops. You'll get 210.025 divided by 9, which is going to give you a 23.336. So your spread of this data, one standard deviation way above, you'd expect to see roughly 68% of all observations above and below, 23 above and 23 below your grand mean of 13. Which kind of gives me this indication that these different diets that I was seeing isn't really too far away. If my standard deviation is at 23, then being off by 1 or 2 from the grand mean is not probably going to be that big of a value, that big of a difference. So with all of that being said, what questions do you have for me?
Where did you get the -1? You have the number of observations -1.
Mm-hmm.
That's from the, which is what you do.
Yeah, I don't have a great motivation because it's essentially a correcting term for trying to connect uneven group numbers and get a standard deviation for it. There is a high level explanation that I just don't know off the top of my head though.
But basically, it's always going to be -1.
Mm-hmm. Always -1. Actually, wait, no. How do you calculate standard deviation? Essentially what you're
-1.
Yeah. So standard deviation in general was the sum from all of your observations how far it deviates from the mean squared divided by n-1. Really what you're doing is you're eliminating that division of n-1 by each of those terms from the formula. And then you're then going to be dividing out by a new number, which is the total number of observations you have minus the total number of groups. And the total minusing the total number of groups is because for each group that you add, you lose a degree of freedom. That's where it's coming from. All right, any other questions? All right. Well, we have our data, we have a grand mean, and we have a pooled standard deviation, and that's given us this idea that, hey, it doesn't seem, based on the standard deviation, that those means for each of our diets is too far off from what the grand mean is, indicating that we're not really seeing too much of a significant effect from each of these diets. There's small differences, but nothing really of note. So we want a way to say, okay, I want to fully test this out. Say, not if it's just coming from just the sample, but if I want to relate this to a population, right, and some sampling distributions, how often would I expect to see data like this? So there's something called the ANOVA table. ANOVA table is all the information you're going to need to calculate what is called the F statistic. It's just a bunch of different formulas, and you're going to need the sum of squares and the mean square between groups and within groups. So with the time, I can break this down. I think the main takeaway I want you to see here is what's going to be important is degrees of freedom. So if you're talking about between groups, really what you're saying is group 1, group 2, group 3, and group 4. So if I look at the groups as my observations, the total number of degrees of freedom I have would be the total number of groups minus 1. And what we're doing here is for this sum of squares, essentially kind of doing a pseudo standard deviation calculation or variance calculation, is we're saying, okay, how far does the sample mean for that group deviate from the overall mean, the grand mean for the entire data set that I'm looking at? So I take that difference and I square it, multiply it by that sample size, and add each of those up together. Once I have that, I'm looking for the mean of those sum of squares, called the mean square. So I just take each one of those sum of squares, add them all up together, and divide by the total number of sum of squares, which is i.e. my degrees of freedom, which is that I minus 1. That's going to be the same case for each of these mean squares, but if I'm looking within a group, okay, so instead of doing that, looking at it with the observation minus the mean. So again, this SI squared here, sum from I equals 1 to n, or j equals 1 to ni of y ij minus y I bar, so that sample mean squared divided by an I minus 1. So what we're saying here is we're now going to be comparing the observation to each of those diet means or those sample means, taking that difference and squaring it, and then I want to calculate whatever that sum of squared is divided by the degrees of freedom. When I do it in that manner, my degrees of freedom is just going to be the total number of observations I had minus the number of groups. So that when I add all of these together, I'm going to get these certain totals. Well, the first total, and this is just kind of a way to make sure I balance out all this information. First total is just going to be the number of observations that I have minus 1. And that's just coming from taking the degrees of freedom from between groups, I minus 1, and adding to it the total degrees of freedom for within groups. When I add this, well, I'll have an I minus a 1 plus the n dot minus an I. Those i's cancel each other out, leave me with that n dot minus 1. So that's where that total comes through. And if you want to take the time and play around with this sum of squares notation and the summation notation, what you end up doing is recognizing that the total is going to be just, you're taking each observation from each group, subtracting its difference from that grand total, and then squaring it. Now, again, when we get to the point where we're going to want to calculate the p-value, these mean squares are the most important. So your mean squares from between groups and within groups. Okay. So we're gonna get an example of doing this. Looks like not today, it'll be Monday. These were all the calculations that you're gonna need for your analysis of variance. Because what the analysis of variance model is essentially saying is that, okay, well, when we're looking at each observation, under that assumption that all of my population means for each group are the same, that null hypothesis, I can just call that a grand population mean, which I just represent as mu. It doesn't matter whether I was in diet 1, diet 2, or diet 3, or group 1, group 2, group 3, group 4, group 5, whatever. Those group means should be the same thing as the population mean. So that I can view every single observation as whatever the population mean is, plus these two values. You're going to see this tau and this epsilon. The tau is just representing the effect from being in that particular group, right? We would expect that there's still some overall mean for the entirety of this data, regardless of which group you're in. But then depending upon which group, there's probably going to be some added or subtracted effect. Right? I could be adding or subtracting a 1 or adding or subtracting a 2 to the total mean. And then this epsilon right there is just saying, hey, it's never going to be absolutely perfect because the real world isn't perfect. So there's going to be some small random error that's going to occur. But each observation comes from taking the grand mean from the population, adding in some treatment effect, and then just a little bit of error. So when we do that, really what we're saying when we're making this assumption of that all these means are the same across all these different treatment groups is that that treatment effect, that little tau, is going to be the same. Now, it might be adding, they might all be adding to whatever the population mean is, they might all be subtracting, but the effect itself is all the same. So what we want to do is then figure out, okay, well, is there a significant treatment effect? That error is going to be something we want to be as close to 0 as possible, i.e. that epsilon. But will there be a difference? So we get all of these estimators, right? Greek letters indicate that it's coming from a population, but I don't want to ever, when I'm doing sample data, I never actually get the entire population. I only get estimates to those population parameters. So then I'm just going to let that grand mean that I get from my data be my estimator for what the entirety, regardless of groups, mean will be. And then those treatment effects just become the difference in the mean for the group and the grand mean. Again, that idea of how far does this group's mean deviate from what we see overall. When we put all these together, we get that same approximation, right? If I play with this and do the little bit of algebra, I'm adding and subtracting the means for each of the populations, and I'm adding in the observation for each groups. What I get is just this approximation, and this is what the model is trying to say. Well, I can approximate from my sample data what each observation should be based on the grand mean plus some potential treatment effect and then a little bit of error that I'm going to see because this is a real world example. So what we're going to do today is just say, hey, for that same data, let's estimate what the treatment effect is. So estimate what happens when applying diet 1 or diet 2 or diet 3. So same data, we have our same means for each of the samples. What was our grand mean for this data?
13.
Yeah, 13. Okay. So then I want to find the treatment effect for the first group. To find the treatment effect for the first group, the estimate for it, I just take that group's sample mean and subtract the grand mean from it. So for the first group, I'm going to take its sample mean, which is what? 11. And then I'll subtract the grand mean, which is 13. And 11 minus 13 is -2. What is the estimated treatment effect for the second group? Well, what was the observed sample mean for that second diet? 15. And I subtract my grand total, my grand mean, which is 13, giving me what? 2. And then diet 3, well, that's going to be a 12 minus a 13, which gives me a -1. So of these 3 groups, if I'm comparing them as there's no difference between the diets, right, with that assumption, and I look at, okay, is a difference between the 3 diets, which one seemed to be doing the best? Which one had a best treatment effect? Diet 2. Because with that treatment, I was gaining 2 pounds versus if I just, or when I consider all 3 diets the same, there seems to be an increase of 2 from there. Whereas the other 2 diets, diets 1 and diet 3, there is some small decrease. So we'd expect that, okay, maybe if there is going to be something that works a little bit better, it might be diet 2. But across the board, adding 2, subtracting 2, and subtracting 1, there's not too much of a difference there. So we want to say a way that we can scale this to any general type of scenario and say, okay, these treatment differences that we see, are those differences significant enough? Or is this probably just due to some randomization from the sample? That is going to be the global F test. So we'll talk about that on Monday, as we don't have class on Friday. But the global F test just says, hey, I'm going to compare it to a F distribution, which is a very popular distribution. You have T distribution, Gaussian, some popular distributions, T distribution, chi-square distribution, F distribution, Gaussian distribution, Poisson distribution are some names that you probably have heard somewhere. Okay, what distribution you use is depending on the data itself and what field you're applying in. But you're going to calculate an F statistic, and that F statistic just depends on that mean squared of the between groups. You're going to divide it by the mean squared within groups. So those calculations that we were getting from that ANOVA table. That's going to give you an F statistic with 2 degrees of freedom. So you have for the numerator and denominator, I'll compare that to an F distribution, and then we'll be able to get a p-value. Okay? And that is our way to then determine whether or not some of this differencing that we saw with the treatment effects from the samples is something of significance, or if it's probably just due to some small randomization in sample. So that is there if you want to look at it before class on Monday. And then on Monday, we'll also talk about two-way ANOVA. So essentially, just if you have multiple factors, so instead of, let's say, diet 1, diet 2, diet 3, you also added in location 1, 2, and 3. So you had mixed treatments. There'll be a two-way ANOVA, and the setup is roughly the same. And we'll talk about on Monday how to do all of these in R as well. Okay, because as you can kind of see, some of these calculations, if you get larger data sets, are not going to be nice to do by hand. So if you have questions for me, feel free, stick around and ask them. But I'm already 3 minutes over, so if you don't have any questions for me, feel free to get on out of here, and I'll see you next Monday.
Have a good holiday, Ken.
Thank you, too.
Can we scroll back up to, like, I guess the S pool, the number you ended up getting, 20, 23.
Okay.